Welcome, focused learners, to this explainer. Today, we're taking an incredible journey from the literal ground beneath our feet all the way up to the stars. We're going to create a comprehensive but totally engaging 10-minute summary of Chapter 1, Gravitation. Get ready to break down the classic physics that hold our entire universe together. Let's just dive right in. Here's our quick roadmap for today. We're covering Newton's universal law, gravitational field strength, variations of gravity, satellites and orbits, and finally, gravitational potential.
All right, starting off with Section 1, Newton's universal law.
Okay, let's lay our foundation by focusing on the classic physics principles that keep us all firmly anchored to the ground. You know, Newton's law of universal gravitation. At its core, there's a direct relation. The gravitational force between two objects is directly proportional to the product of their two masses. But, and this is the kicker, that force is inversely proportional to the square of the distance between them. We use the letter r squared for this, because gravity spreads out in all directions in three-dimensional space. So the larger that sphere of influence gets, the more diluted the force becomes. Which brings us to an absolutely crucial concept, the inverse square law. Now, this isn't just some mathematical quirk, it's a physical reality of how our universe operates. As the distance between two objects increases, the gravitational pull doesn't just slowly fade away, it drops off drastically. Like, if you double the distance, the force becomes a quarter of what it was. It becomes weaker very, very quickly, exactly according to the square of the distance. Moving on to Section 2, decoding gravitational field strength.
So we know mass attracts mass, right? But how does an object actually feel this pull across totally empty space? Well, to understand this, we need to clearly define our terms. Gravitational field strength, which we represent with a lowercase g, is simply the region or area around a mass where gravitational force acts. If you pop a test mass into this invisible field, it'll experience a force. And because it's a force per unit of mass, we measure this field strength in newtons per kilogram. Definitely lock that vocabulary away in your memory.
Now, a fascinating question comes up here. Why do we treat the Earth as a single point mass in space? I mean, it's huge. Well, the answer is incredibly elegant. The Earth is a sphere, and it has these symmetrical field lines all around it. The distribution of those field lines is uniform, and its mass distribution is generally uniform too. Because of this perfect symmetry, mathematically and physically speaking, the entire mass of Earth behaves exactly as if all its mass were concentrated at one single, microscopic point right at its very center. Pretty wild, right?
So here is the real takeaway. When we derive the formula for g on the surface of the Earth, we see it equals the gravitational constant, capital G, multiplied by the mass of the Earth and then divided by the radius of the Earth squared. Notice what's missing from that final equation? The mass of the actual object that's falling. The strength of the field, the value of lowercase g, depends entirely on the mass and radius of the Earth itself. It does not depend on the mass of the falling object. This is exactly why a bowling ball and a feather will fall at the exact same rate in a vacuum.
Next up, Section 3. Variations of gravity. Let's move our narrative upward and inward now. We kind of tend to think of gravity as this constant 9.8 meters per second squared everywhere, but nature is way more dynamic than that. Let's challenge a common assumption with a specific question straight from the curriculum. Why is the value of g actually lower at the equator than it is at the poles? If Earth is Earth, shouldn't gravity just be the same everywhere you stand? Well, there are actually two main culprits behind this variation. First off, distance. The Earth isn't a perfect sphere. It kind of bulges at the middle. Therefore, the equator is simply further away from the center of the Earth than the poles are, making g weaker based on that inverse square law we covered just a minute ago. Second, the Earth is spinning. This rotation creates a centrifugal force at the equator, literally a pushing force that acts against gravity. If the Earth suddenly stopped spinning, this centrifugal factor would vanish, and the value of gravity at the equator would instantly increase. This leads to an even more counterintuitive scenario. What happens to gravity if we dig straight down? As you move towards the center of the Earth, the amount of Earth's mass below you actually decreases. By the time you reach the exact center of the Earth, all of the mass around you is perfectly uniform. The attractive forces pull you equally from every single direction, completely balancing each other out. This means at the very center of the Earth, the net value of g drops to exactly 0. You'd be weightless. Okay, so we just went down. Now let's go up. As we move away from Earth into higher altitude, gravity drops rapidly. Let's use our inverse square logic step by step. Step 1, you have your original surface gravity. Step 2, you fly up into space to an altitude exactly equal to 1 Earth radius. That means you are now twice as far from the center of the Earth as you were when you were standing on the surface. Step 3, because distance is squared, doubling your distance means gravity drops to 1/4 of its surface value. 2 squared is 4, so your gravitational pull is divided by 4.
Moving right along to Section 4, Satellites in Orbits. It's time to break completely free of the Earth's surface and transition into the high-speed realm of orbital physics. Believe it or not, the idea of artificial satellites isn't new. It actually goes all the way back to Isaac Newton in the 1600s. He proposed this brilliant thought experiment. Imagine shooting a cannonball off a mountain, perfectly parallel to the ground. It travels forward, but gravity pulls it down, so it eventually hits the Earth. But what if you shoot it so incredibly fast that as gravity pulls it down 5 meters, the curvature of the spherical Earth also drops away by exactly 5 meters? The cannonball would be constantly falling, but the ground would just keep curving away from it. It would never hit the ground. It would become a satellite.
For this magic to happen near Earth's surface, the object needs an incredible minimum speed, specifically 8 kilometers per second. That is the critical orbital velocity required so that the horizontal distance covered perfectly matches the downward deviation caused by gravity. That 8 kilometers per second is literally the magic number keeping our modern communication and weather satellites aloft today.
But managing these orbits gets kind of tricky. Here's another really fascinating question. Imagine 2 satellites orbiting Earth in the exact same path and direction. If the satellite behind the other decides to hit the gas and accelerate, will it smash into the satellite in front of it? What do you think?
The answer builds a much deeper understanding of orbital mechanics. If that satellite in the back speeds up, it actually doesn't just go faster on the exact same path. Gaining speed pushes it outward into a wider, higher orbit around the Earth. Because its new orbital path is larger and farther away, it completely avoids the satellite in front of it. The distance between their orbital paths will just go on increasing. Crisis averted.
And finally, Section 5, Understanding Gravitational Potential. For a final conceptual leap today, we're going to look out beyond orbits, moving all the way toward infinity. We learned early in physics that potential energy equals mass times gravity times height, or PE equals mgh. So, if we already have this tidy little formula, why on earth do we need the complicated concept of gravitational potential?
Well, the answer lies in a critical limitation. We use mgh on Earth because we assume g is constant. But when we talk about launching rockets into deep space, the height becomes almost infinite. At those massive distances, g isn't constant anymore. It rapidly drops towards 0. If you plug 0 for g into mgh, the whole equation just collapses. Because the force of attraction is constantly changing as you move further away, we actually have to calculate the work done in tiny individual segments using the integration of forces.
This brings us to the formal definition of absolute potential energy. It is the amount of work done in moving a body from Earth's surface to a point at infinite distance where the value of g is negligible. Think of it as the total energetic cost to entirely break a body free from Earth's gravitational grip and put it at an infinite distance away. And that leaves us with a pretty profound thought to end on. If we launch an object at about 11 to 12 kilometers per second, which is our escape velocity, it will completely break free of Earth's gravitational field forever. But when an object finally reaches that theoretical infinite distance where Earth's gravity can no longer touch it, what happens to its absolute potential energy? Does it cap out? Does it reach absolute zero? It's a reminder of just how vast and mathematically beautiful the universe truly is. Thanks for joining me on this explainer. Keep asking those big questions, and I'll catch you on the next deep dive.